In chapters 5 and 6, we examine the concept of a random variable and its distribution defined by a function. The function is either called a probability distribution function, PDF, for chapter 5, which looks at discrete random variables, or it's called a probability density function for chapter 6, where the random variable is continuous. In chapter 5, the function called the probability distribution function, or PDF, is denoted f of x, an f with parentheses around it and x. F of x is equal to the probability of x. F of x is the height of the distribution at x. In chapter 5, the probability of x being less than 4 may be equal to the probability of x being less than or equal to 4, or not. Whether these inequalities equal or not depends on the particular probability distribution function. This is because x is a discrete random variable in chapter 5. An example of one is the number of cans of Coca-Cola sold by a gas station. The reason why number of cans is a discrete random variable is because the gas station could sell 1 can or 2 cans. It can't sell a half can. It can sell 10 cans or 11 cans, but it can't sell 10 and a half cans. In chapter 6, x is a continuous random variable. The volume of gasoline sold by the gas station is an example of a continuous random variable. For example, the gas station could sell 10 gallons of gas, 11 gallons of gas. It could sell 10.5 gallons of gas. It could sell 10.1 gallons of gas. It could sell 10.001 gallons of gas. It could sell 10.0000001 gallons of gas. And we continue doing that. That's why it's called a continuous random variable. In chapter 6, f of x is a probability density function, which we still call a PDF. In chapter 6, f of x is not equal to the probability of x, but the areas under f's graph represent probabilities. F of x is still the height of the distribution at x in chapter 6. In chapter 6, the probability of x being less than, say, 4, that's the same as the probability of x being less than or equal to 4. A discrete random variable's probability distribution function is associated with a mean and a standard deviation. The same goes for a continuous random variable's probability density function. It too is associated with its own mean and standard deviation. Discrete random variables can be countable and finite or countable and infinite. Let x be the number of TVs sold at JSL appliances in a given day. X can take on the values of 0, 1, 2, 3, or 4. We can count the TVs sold each day at JSL appliances. And there is a finite upper limit on the number of TVs that could be sold on a given day, which is a result of there only being so much room in the stockroom. Let x be the number of customers arriving in one day. Here, x can take on infinite many values, starting at 0, going to 1, going to 2, going to 3, going to 4, etc., etc., etc. We can count the customers arriving, but there is really no finite upper limit on the number of customers that might come in on a given day. Suppose you have 60,000 people, how large their families are, and x is defined to be the number of dependents reported on a tax return. That is an example of a discrete random variable. Suppose you ask the same people, how much water did you buy? If x is defined by the number of bottles of water you purchase in a month, that is a discrete random variable, because you can buy, say, 10, you can buy 11, but you can't buy 10.5. If the question is how much water do you drink in a day, and x equals ounces of water you drink in a day, that's continuous, because you could drink 10 ounces of water in a day, you could drink 11 ounces of water in a day, you could drink 10.5 ounces of water in a day, you could drink 10.1 ounces of water in a day, you could drink 10.00001 ounces in a given day, and you can continue doing that, which is why this is a continuous random variable. Suppose the question is distance from home to store. If x is defined to be distance in miles from home to store, then this would be a continuous random variable because your distance might be 5 miles, it might be 4 miles, it could be 4.5 miles, it could be 4.01 miles, it could be 4.00001 miles. So that would be an example of a continuous random variable. The probability distribution is defined by a probability function. In Chapter 5, this function is a probability distribution function. But in Chapter 6, it is a probability density function. The function is typically denoted f of x, which provides the probability for each value of random variable x. The required conditions for a discrete probability function are identical to properties of relative frequencies, which include f of x is greater than or equal to 0. This is similar to the fact that relative frequencies are between 0 and 1. Summing up f of x for all values of random variable x equals 1. This is similar to the fact that the relative frequencies add up to 1. In this example, past data on TV sales is used to build a frequency table, and then we use these to compute relative frequencies, which we interpret in this chapter as a discrete probability distribution for TV sales. According to the frequency table, JSL appliances sold 0 TVs on 80 of the previous 200 days, 1 TV on 50 of the previous 200 days, 2 TVs on 40 of the previous 200 days, 3 TVs on 10 of the previous 200 days, and 4 TVs on 20 of the previous 200 days. If we define the number of TVs sold as a random variable, denoted by the letter x, then f of 0, or the probability the store sells 0 TVs, is 80 divided by 200, which equals 40. F of 1, or the probability the store sells 1 television, is 50 divided by 200, which equals 0.25. F of 2, or the probability the store sells 2 TVs, is 40 divided by 200, which equals 0.2. F of 3, or the probability the store sells 3 TVs, is 10 divided by 200, which equals 0.05. F of 4, or the probability the store sells 4 TVs, is 20 divided by 200, which equals 0.1. Notice that all of the probabilities are between 0 and 1, and their sum equals 1. The discrete probability distribution of JSL TVs sold example is graphed below. Since f of 0, or the probability the store sells 0 TVs, equals 0.4, the height of the discrete probability distribution at x equals 0 is 0.4. Since f of 1, or the probability the store sells 1 TV, equals 0.25, the height of the discrete probability distribution at x equal 1 is 0.25. Since f of 2, or the probability the store sells 2 TVs, equals 0.2, the height of the discrete probability distribution at x equal 2 is 0.2. Since f of 3, or the probability the store sells 3 TVs, equals 0.05, the height of the discrete probability distribution at x equals 3 is 0.05. Since f of 4, or the probability the store sells 4 TVs, equals 0.10, the height of the discrete probability distribution at x equals 4 is 0.1. The expected value of random variable x is denoted mu, and is found by multiplying the values of random variable x with the corresponding probabilities and then summing these up. The values of x are in blue. The probabilities that are associated with those x's are in red. And then we sum them up over n. The variance summarizes the variability in the values of random variable x. The variance of random variable x is denoted sigma squared. It is computed by first subtracting the mean from each value of x, squaring these deviations from the mean, and then multiplying each deviation by the probability, which is shown in red. We can use the expected value equation from the previous slide to compute the expected value of any discrete probability distribution. Consider our distribution of TVs sold in the JSL example, which indicated that the probability the store sells 0 TVs is 0.4, one TV is 0.25, and so on. After multiplying the values of x with its probability, we sum these up. The first product is x times its probability of 0.40, which is 0.00. The second product is the second value of x, 1, times its probability, 0.25, which is 0.25. Then we take 2 times its probability, 0.20, which is 0.40. Then we take 3 times 0.05, which is 0.15. And then 4 times its probability of 0.1, which is 0.40. The sum of this column is called the expected value of x. On any given day, they expect to sell 1.2 TVs. The variance is found by subtracting the mean of 1.2 from each of the values of random variable x. The first deviation from the mean is equal to 0 minus 1.2, which equals a negative 1.2. The second deviation from the mean is equal to 1 minus 1.2, which equals a negative 0.2. The third deviation from the mean is equal to 2 minus 1.2, which equals 0.8. The fourth deviation from the mean is equal to 3 minus 1.2, which equals 1.8. The fifth deviation from the mean is equal to 4 minus 1.2, which equals 2.8. The first square deviation from the mean is equal to negative 1.2 squared, which equals 1.44. The second squared deviation from the mean is equal to negative 0.2 squared, which equals 0.04. The third square deviation from the mean is equal to 0.8 squared, which equals 0.64. The fourth square deviation from the mean is equal to 1.8 squared, which equals 3.24. The fifth square deviation from the mean is equal to 2.8 squared, which equals 7.84. In the final column, we multiply the square deviations by the corresponding probabilities. The probabilities are in the f of x column. The first, which is equal to 1.44 times the probability of 0.4, which equals 0.576. The product of the second squared deviation from the mean, 0.04, and the corresponding probability, 0.25, equals 0.01. The product of the third square deviation from the mean, 0.64, and its corresponding probability of 0.2 equals 0.128. The product of the fourth squared deviation from the mean, 3.24, and its corresponding probability of 0.05 equals 0.162. The product of the fifth squared deviation from the mean, 7.84, and the corresponding probability, 0.1, equals 0.784. The sum of the last column is 1.660. This is the variance of daily TV sales, which is in units of TV squared. Taking the square root of 1.660's TV squared is the standard deviation of daily TV sales, which equals 1.2884 TVs. The discrete uniform probability distribution is the simplest example of a discrete probability distribution given by a formula. It is not covered in the textbook, but the continuous version is covered in Chapter 6. The discrete uniform probability distribution function, PDF, is f of x equals 1 divided by n, where n is the number of values the random variable may assume. The function implies the values of the random variable are equally likely to occur, hence the name uniform. In this example, we construct a probability distribution for the rolling of a die. The random variable x can be taken on one of the following values, 1, 2, 3, 4, 5, or 6. Because a typical die has 6 sides, with these values on each side, what are the probabilities of these events? What is the expected value and variance of this random variable? The probabilities of the outcome are equal because n is equal to 6, and the probability distribution function is 1 divided by 6. F of 1, the probability of rolling a 1, equals 1 divided by 6. F of 2, the probability of rolling a 2, equals 1 divided by 6. F of 3, the probability of rolling a 3, equals 1 divided by 6. F of 4, the probability of rolling a 4, equals 1 divided by 6. F of 5, the probability of rolling a 5, equals 1 divided by 6. F of 6, the probability of rolling a 6, equals 1 divided by 6. For any discrete uniform random variable, starting at 1 that increases by 1 to n, the expected value is n plus 1 divided by 2. The variance is the difference in n squared and 1 divided by 12. The standard deviation is the square root of the variance. For our die example, n equals 6, hence the expected value is the sum of 6 and 1 divided by 2, which is 3.5. The variance is the difference in 6 squared and 1 divided by 12, which is 2.9167. The standard deviation is the positive square root of the variance, which is 1.708. Recall that we can compute the expected value of any discrete random variable. The expected value is computed by summing up the products of the values of the random variable and their respective probabilities. In the table below, we compute 6 such products. The first is 1 times its probability of 0.1667, which equals 0.1667. 2 times its probability of 0.1667, which equals 0.3333. 3 times its probability of 0.1667, which equals 0.50. 4 times its probability of 0.1667, which equals 0.667. The fifth product is 5 times its probability of 0.1667, which equals 0.8333. The final sixth product is 6 times 0.1667, which equals 1.0. Now notice all of the values in the probability column, labeled f of x, are the same. And each one of these values is 1 divided by 6 to 4 significant digits. The sum of the final column is the expected value, which is the same as we found when we used the shortcut formula n plus 1 divided by 2. So the expected roll of the die is 3.5. Recall we can compute the variance of any discrete random variable. We first must compute the deviations from the mean. There are 6 of these in the rolling the die example. With the mean being equal to 3.5, the first deviation from the mean is a negative 2.5. We take 1 minus 3.5, we get a negative 2.5. The second deviation from the mean is 2 minus 3.5, which is a negative 1.5. The third deviation from the mean is 3 minus 3.5, which is a negative 0.5. The fourth deviation from the mean is 4 minus 3.5, which is 0.5. The fifth deviation from the mean is 5 minus 3.5, which is 1.5. The sixth deviation from the mean is 6 minus 3.5, which is 2.5. Next, we square the deviations from the mean. The first square deviation of the mean is found by squaring negative 2.5, which is 6.25. The second squared deviation from the mean is found by squaring negative 1.5, which equals 2.25. The third squared deviation from the mean is found by squaring negative 0.5, which equals 0.25. The fourth squared deviation from the mean is found by squaring 0.5, which is 0.25. The fifth squared deviation from the mean is found by squaring 1.5, which equals 2.25. The sixth squared deviation from the mean is found by squaring 2.5, which yields 6.25. Next, we calculate the products of the squared deviations from the mean and its corresponding probability. And the probabilities do not change. So we're multiplying the two numbers in the boxes all the way down the columns. When you sum the final column, you get the variance of rolling a die. The variance of rolling the die is 2.9167, which is exactly what we found when we used the shortcut equation. The standard deviation is just the positive square root of the variance. The standard deviation of rolling die is 1.7078. The binomial probability distribution is a common discrete probability distribution function. Its 4 properties are, number 1, the experiment consists of a sequence of n identical trials. For example, randomly picking 20 male students from the campus directory is a sequence of 20 identical trials. Number two outcomes, success and failure, are possible on each trial. Suppose you are interested in putting together an intramural basketball team to compete in the university's Winter Basketball League for male students. If you pick 20 male students at random from the campus directory, some of them will have game while others won't. Having game is a success for this experiment, while not having it is a failure. Number three, the probability of success denoted by P does not change from trial to trial. Suppose a graduate and a member of your fraternity tells you that over the last 10 years, 15% of males enrolled in the university were starters on their high school basketball teams. If you randomly pick 20 male students from the campus directory, the probability that each has game is 0.15, while the probability that they don't have game is 0.85. And it doesn't change from trial to trial. Number four, the trials are independent. Randomly picking 20 male students from the campus directory means those that make the list represent 20 independent trials. If, on the other hand, you selected the 20 male students from a group that were playing ball at the rec center, the 20 selected would not be independently chosen. In the binomial probability distribution problem, our interest is in the number of successes occurring in the n trials. For the basketball example, our interest is in the number of male students that have game out of the 20 that were selected randomly from the campus directory. We let X denote the number of successes occurring in the n trials. If 5 of the 20 male students you choose randomly from the campus directory had game, then X is equal to 5. X can take on n values, actually n plus 1 values, 0, 1, 2, 3, yada yada yada, out to 20. In our example, n is equal to 20. Hence, the binomial probability distribution are associated with discrete random variables with a finite number of values. The binomial probability distribution function is given by the following equation. F of x represents the probability of x successes in n trials. If you need 5 male students to fill an intramural basketball team, and you randomly chose 20 male students from the campus directory, f of 5 gives you the probability of 5 successes in 20 trials. N is the number of trials, hence n minus x is the number of failures, because there is only success and failure in a binomial experiment. If x equals 5, the number of male students that don't have game is 15. Thus, with n equal 20, x equal 5, n minus x is 15. P is the probability of success. Again, since there is only success and failure in a binomial experiment, 1 minus p is the probability of failure. The probability that a person in your sample of 5 male students has game is 0.15. The probability the first person in your sample of 5 male students doesn't have game is 0.85. These probabilities do not change from the first to the 20th male students in your sample. The first part of the binomial equation is circled in red and highlighted in yellow. It represents the number of different sequences providing x successes and n minus x failures. If 5 male students are picked at random from a campus directory and 1 had game, then there are 5 ways to order a sequence of 1 success, those with game, and 4 failures, those without game. Because 5 factorial divided by the product of 1 factorial and 5 minus 1, or 4 factorial, equals 5, there are 5 ways to order 1 success. The 5 sequences are success, then 4 failures, a failure, success, and then 3 failures, 2 failures, a success, 2 failures, 3 failures, a success, and 1 failure, 4 failures, and 1 success. The x factorial in the denominator means order doesn't matter. We talked about this in the previous chapter. The last part of this equation represents the probability of a given sequence with x successes and n minus x failures. Recall there are 5 ways to order a sequence of 1 success, those with game, and 4 failures, those without game. When 5 male students are picked at random from the campus directory, the probability of the 5 sequences are all equal. Evans Electronics is concerned about low retention rate of employees. In recent years, management has seen a turnover of 10% of hourly employees. Thus, for any hourly employee chosen at random, management estimates a probability of 0.1 that the person will leave the company this year. Choosing 3 employees at random, this is the number of trials. What is the probability that 3 of them, the number of successes is the number that follows the phrase, what is the probability? Will leave the company this year. Will leave the company this year is, quote-unquote, success. Hence, the probability of success is 0.1, because 0.1 of the people chosen at random will leave the company this year. This means will not leave the company this year is a failure. Now write what we know. We know the probability of success leaving the company is 0.1. The number of trials is 3. And the number of these 3 that are successes is 3. We plug these into the equation, the binomial equation. Notice that x is in red font in this equation. This is done because x can be equal to 0, 1, 2, or 3. The other letters represent fixed numbers, n equal 3 and p equal 0.1. 3 people are picked at random from the company directory. We want the probability that all 3 will leave the company within the next year. If all 3 of the 3 that were picked leave the company, then none will remain. The first part of the binomial equation is circled in red and highlighted in yellow. It represents the number of different sequences providing 3 successes and 0 failures. There's only one sequence for 3 successes and 0 failures. Success, success, success. That's why this red circle, the value of it equals 1, which is why that is equal to 1. The next part of the equation is the probability of success. Notice we have 3 successes, and that is in the exponent of 0.1. So essentially what this oval is doing is it's taking 0.1, multiplying it by itself, and then multiplying it again by 0.1. In this last oval, we have 0.9 raised to the 0 power, and anything raised to the 0 power is 1. That is a fancy way of saying 1. This is a fancy way of saying 0.1 times 0.1 times 0.1, and that's a fancy way of saying 1. So all that we're doing here is applying the product rule. So the probability of 3 of the 3 people chosen at random leaving the company is 0.001. Outcomes of a binomial distribution can be diagrammed using a tree diagram. In stage 1, the first worker chosen can either stay or leave. Given the first worker will leave, the second worker can stay or leave. Given the first and second workers leave, the third worker can stay or leave. If all 3 workers leave the company, x equals 3. The probability of leave and leave and leave equals 0.1 times 0.1 times 0.1, which is equal to 0.0010. This is the number. This is the same number we computed on the previous slide using the binomial probability distribution function. If the first 2 workers leave, but the third one stays, x equals 2. The probability of leave and stay equals 0.1 times 0.1 times 0.9, which equals 0.009. Given the first worker leaves, but the second person stays, the third worker can stay or leave. If the first worker and the third workers leave, but the second stays, x is equal to 2. The probability of leave and stay and leave equals 0.1 times 0.9 times 0.1, which is equal to 0.0090. If the first worker leaves, but the second and third stay, x equals 1. The probability of leave and stay equals 0.1 times 0.9 times 0.9, which equals 0.0810. Given the first worker stays, the second worker can stay or leave. Given the first worker stays but the second one leaves, the third worker can either stay or leave. If the first worker stays but the second and third leave, x equals 2. The probability of stay and leave equals 0.9 times 0.1 times 0.1, which equals 0.0090. If the first worker and third stay, but the second leaves, x equals 1. The probability of stay and leave and stay equals 0.9 times 0.1 times 0.9, which is equal to 0.0810. Given the first two workers stay, the third could stay or leave. If the first two workers stay, but the third leaves, x equals 1. The probability of stay and leave equals 0.9 times 0.9 times 0.1, which is equal to 0.0810. If the three workers stay, x equals 0. The probability of stay equals 0.9 times 0.9 times 0.9, which is equal to 0.7290. Since there are three sequences of one success and two failures, and each of these sequences have the same probability of occurring, 0.0810, the value in the red oval would be equal to 3, because there are three sequences of one success and two failures. The value in the red oval is equal to 0.0810. All that the binomial distribution function does is it takes the number of sequences, in this case 3, and multiplies by the probability of each sequence, which are identical. Adding up these probabilities yields the probability of leave and stay, plus the probability of stay and leave and stay, plus the probability of stay and leave, which equals 0.243. This is the exact same number we'd get if we used the binomial probability distribution function with x equal to 1, n equal to 3, and p equal to 0.1. To compute the expected value and variance of a binomial probability distribution, we can use the following equations or the following shortcuts. The expected value, mu, equals the number of trials times probability of success. The variance takes the mu and multiplies it by the probability of failure, n times p, mu, times 1 minus p, the probability of failure. The standard deviation is just the positive square root of the variance. In the Evans electronic example, n equals 3 and p equals 0.1. Hence, the expected value is 3 times 0.1, which is 0.3. 0.3 employees out of 3 are expected to leave over the course of the year. The variance is equal to 3 times 0.1 times 1 minus 0.1, which is 0.27. The standard deviation is just a positive square root of the variance, which equals 0.5196. We're going to use the following equations to verify that the shortcut equations are actually giving the correct values for the expected value and the variance of a binomial probability distribution function. To compute the expected value, we first must compute the products of the values of x and their respective probabilities. The probabilities 0.729, 0.243, 0.027, 0.001 were either found using the binomial equation or the tree diagram that we demonstrated earlier. The first product is 0 times 0.729, which is 0.000. The second product is 1 times 0.243, which is 0.243. The third product is 2 times 0.027, which is 0.054. The final product is 3 times 0.001, which is 0.003. Summing that up gives us an expected value of 0.3, which is the same expected value that we got using the shortcut equation. To verify the shortcut variance is actually given us the correct value for the variance, we complete the following table. With a mean equal to 0.3, we subtract it from 0 to get the first deviation from the mean, which is negative 0.3. We subtract 0.3 from 1 to get the second deviation from the mean, which is 0.7. We subtract 0.3 from 2 to get the third deviation from the mean, which is 1.7. We subtract 0.3 from 3 to get the fourth deviation from the mean, which is 2.7. Then we square the first deviation from the mean, the second squared deviation from the mean, the third deviation from the mean, and the fourth deviation from the mean. 2.7 times 2.7 is 7.29. Next, we want to take the square deviation from the mean and multiply by its respective probability. Remember, the probability comes from the binomial distribution function. We plug in n equal 3, p equal 0.1 into the binomial distribution function, and then we plug in 0, 1, 2, and 3, and out comes 0.729, 0.243, 0.027, and 0.001. So the first product is 0.0656. We multiply 0.49, the second square deviation from the mean, times its probability. We get 0.1191. We take the third square deviation from the mean, 2.89, multiply it by its probability, 0.027, and we get 0.0780. We take the fourth square deviation from the mean, 7.29, multiply it by its probability, and we get 0.0073. The variance is the sum of this column, which was the same when we used the shortcut equation. The standard deviation is the positive square root of 0.27, which is 0.5196. We can use the binomial equation to compute the probability of winning the Pick 3 lottery for the evening draw, $1, and exact order. In this lottery, I've chosen number 5 from a list of 10 numbers, 1 from a list of 10 numbers, and 2 from a list of 10 numbers. Because I checked exact, the ping pong balls have to come out in order 5, 1, 2 for me to win $500. Since there are 10 ping pong balls in each jar, the probability of getting a number correct is 1 divided by 10. So the probability of success on each trial is 0.1. Since you pick 3 numbers, and each of these comes from jars containing numbers printed on 10 ping pong balls, there are 3 independent trials. Since you have to pick all 3 to win, all 3 picks have to be successes. None can be failures. Substituting these values into the binomial probability distribution function yields, which simplifies to 1, there's only one sequence that wins, times 0.1 raised to the power of 3. This is the probability of a given sequence, and equals 0.001. Hence, the probability you win is 0.001, but the probability you lose is 0.999. To compute your expected winnings, you add the product of how much you lost and its probability to how much you win and its probability. The probability of winning is 0.001, which can be denoted by F of $499 equal to 0.001. The probability of losing is 0.99, which can be denoted F of minus $1 equal to 0.999. Hence, your expected winnings are minus $1 times 0.99 plus $499 times 0.001, which equals negative 50 cents. So if you buy 20 tickets a week on average, you are losing $10 a week. This means the government has induced you into voluntarily paying an additional tax of $10 a week, which amounts to $520 a year. A Poisson distributed random variable is often useful in estimating the number of occurrences over a specified interval of time or space. It is a discrete random variable that may assume an infinite sequence of values starting at 0 and increasing by 1. That is, x can be equal to 0, 1, 2, 3, 4, 5, 6, 7, 8, yada yada yada. Examples include the number of knot holes on an 8-foot long 2x4, or the number of vehicles arriving at a toll booth in 1 hour. A Poisson experiment has two properties. The probability of an occurrence is the same for any two intervals of equal length. The occurrence or non-occurrence in any interval is independent of the occurrence or non-occurrence in any other interval. The Poisson probability distribution function is f of x equal mu, the mean, raised to the x power, times e to the minus mu, again mu is the mean, divided by x factorial. F of x is the probability of x occurrences in an interval of space or time. Mu is the mean number of occurrences in an interval. E is the number 2.71828, yada yada yada. In the example, patients arrive at the emergency room of Mercy Hospital at the average rate of 3 every 30 minutes on the weekend. This is mu, which is given in every Poisson problem. What is the probability of 4 arrivals in 30 minutes on a weekend evening? 4 is the number of occurrences denoted by the letter x. The value of x always follows the phrase, what is the probability? Mu is equal to 3 and x is equal to 4. Plugging these into the Poisson probability distribution function, f of 4 is equal to 3 raised to the power of 4 times the natural number of e raised to the negative 3 divided by x factorial, in this case 4 factorial, which is equal to 0.1680. In every Poisson problem, mean mu is given. A property of the Poisson probability distribution function is that the mean and variance are equal. In this example, the mean equals the variance, which equals 3. The standard deviation is the square root of 3. We're going to use these equations to verify that property. In the table below, since we computed f of 4 already, it is listed. To compute the mean, we must first compute the products of the values of x and their respective probabilities, f of x. X equal to 4 times its probability, f of 4, which is equal to 0.1680, is 0.6721. Compute the probability of x equals 0, or f of 0. We substitute 0 into the Poisson probability distribution function that is in the top right-hand corner. Doing this yields f of 0 equal to 0.0498. Multiplying this probability by x, evaluating the Poisson probability distribution function at x equal 1, yields f of 1 equal to 0.1494. Multiplying this probability by x equal 1 yields 0.1494. Evaluating the Poisson probability distribution function at x equal 2 yields f of 2 equal to 0.2240. Multiplying this probability by x equal 2 yields 0.4481. Evaluating the Poisson probability distribution function at x equal 3 yields f of 3 equal to 0.2240. Multiplying this probability by x equal 3 yields 0.6721. Summing this column yields 1.9147, which is not equal to the mean of 3. Because a Poisson random variable can take on infinite many numbers starting at 0 and increasing by 1, we need to add more values of x in the table, which I do here. Plugging 11 into the Poisson distribution function yields f of 11 equal to 0.0002. Multiplying that probability by 11 equals 0.0024. Plugging x equal 12 into the probability distribution function gives a probability, or f of 12, equal to 0.0001. Multiplying that by 12 gives 0.0007. Summing that up yields an expected value approximately equal to 3. The sum of this column will never equal 3. It just gets really, really, really close to 3 because x takes on infinite many values. This table will help us verify that the variance of the Poisson probability distribution function is mu. In this case, mu equals 3. The first thing we have to do is we have to take the mean, mu, 3, subtract it from 0. When we do that, we get minus 3.00. Squaring the first deviation from the mean, minus 3 squared, equals 9. Multiplying that 9 by the probability f of 0, which equals 0.0498, yields 0.4481. Minus 2 comes from taking 3 and subtracting it from 1. Squaring minus 2 gives 4. 4 times f of 1, the probability that x equal 1, which is 0.1494, equals 0.5974. Minus 1 here comes from subtracting 3 from 2. Squaring minus 1 yields 1. 1 times f of 2, or the probability that x equal 2, which is 0.2240, is 0.2240. Subtracting 3 from 3 gives 0. 0 squared is 0. 0 times f of 3, 0.2240, is 0. 4 minus 3 is 1. 1 squared is 1. 1 times f of 4, 0.1680, is 0.1680. Sum in this column does not give you 3. It should give you 3, but again, x in a Poisson distribution can take on infinite many numbers, so we need more x's. 8 is from subtracting 3 from 4. 8 squared is 64. 64 times f of 11 is 0.0141. This 9 comes from subtracting 3 from 12. 9 squared is 81. 81 times f of 12 is 0.0045. When we have x up to 12, the variance is approximately equal to 3. Yet again, it will never equal 3 because, again, x can take on infinite many values. So it gets closer and closer and closer to 3.